Hello everyone. Welcome to a Zoom session for Engineering MENG 260, Introduction to Thermal Sciences. Today is June 9. Hope everybody is doing great. And today we're going to lecture on Chapter 5, Introduction to or Control Volume Energy Analysis. Okay, Control Volume Energy Analysis. I have received your exam, no problem, but I need to sit down and grade them, okay? I've already graded 10, so for 10, I was able to do that because there's 8 problems I have to spend at least 15 minutes or 20 minutes trying to go through one by one and see how you are doing on the exam, okay? Most of you have done a great job. So some of you were using a terminology that we have not used in the textbook. I don't know where you got that. So I was a little bit surprised of some of the stuff that you are using that we have never talked about that in this for this class so far. But anyway, so in order to solve math problems, there might be several ways to solve the math problem. Engineering is the same way. There are different approaches. And I think if you know what you're doing, then the answer will be the same. But in some situation, if your assumption is way off, then you won't be able to get the same answer. Remember that internal energy and enthalpy, those are the 2 thermodynamics properties. Always think of enthalpy for open system, okay? Open system. For liquid, try not to use ideal gas law because it gives you a lot of error, okay? So m dot, for example, times delta H, or let me just go back a little bit. If you have an ideal gas law, we said we have delta U is equals to mCV delta T. Okay, mCV delta T. If that's for a closed system. For open system, change in internal energy is equal to mCP times delta T. Okay, so that's what we have. Now, when we are dealing with enthalpy, because enthalpy is equal to internal energy plus PV, okay, PV work. So we have used conservation of energy, which is the first law of thermodynamics. And also we're going to use the second law of thermodynamics, which is entropy, later on chapter 6. On chapter 5 is a conservation of mass, okay, conservation of mass. So we're going to talk about the mass flow rate and volume flow rate, okay, mass flow rate and volume flow rate. And this will be also an introduction to fluid mechanics later on. We have not talked about the fluids yet, so we are going to discuss the control volume and mass flow rate, okay, conservation of mass flow rate. So if we have a system, we have inlet, and then we have exit. And then this dash line, we call it the control volume boundary, okay? Control volume boundary. So time rate, okay, when we say time rate of change of mass contained within the control volume at time t is equals to time rate of flow of mass going into the system, okay, or across inlet I at time t minus the time rate of flow of mass out across exit E. E means exit, I means inlet, okay. So the rate of the flow, which is, we call it the mass flow rate inlet minus the mass flow rate outlet. In most devices, we have 1 inlet, 1 outlet. Sometimes we have 2 inlet, 1 exit. So we're going to talk about the conservation of mass. So it has to be balanced, okay? Balanced. The amount that comes in equals to the amount that goes out. Okay? All right. So So this is the governing equation, and change in mass for the control volume over dt equals to m dot I minus m dot E. That's the mass flow rate, m dot. So one-dimensional flow, this is also when we are dealing with heat transfer, we're going to have a flow that we need to measure with when or fluid mechanics and heat transfer, because we're going to have a laminar flow and we have a turbulent flow. So we need to understand the language of laminar flow. How do we know it's laminar, and how do we know it's turbulent flow? And then we have a velocity profile. So in fluid mechanics, when we have internal flow and then we have external flow. So in this case, when we have a one-dimensional flow, that's a velocity profile. And then for the inlet, the properties of the inlet, for example, we have the air going inside the pipe here, okay, air compressor. So we have the area of the circular shape or round shape, which is a pi d square over 4 or pi r square. And then we have an inlet velocity or V, and then temperature and a specific volume. Okay. Flow is normal to the boundary at locations where mass enters or exits the control volume. All intensive properties are uniform with position over each inlet or exit area through which matters flow. So we're going to be talking about different types of thermodynamic devices, such as compressor, pump, turbine, heat exchanger, nozzle, diffuser, throttling valve, and so on. Okay, all right. So we're going to cover a bunch of topics, which is we call it thermodynamic devices. Okay, which is turbine and compressor and pump for time being. Okay, and before we start, let's just talk about the nozzles and diffusers. Okay, a steady state mass, rate balance, steady state. Okay. Also, let's just do this. A steady state. Okay, this is very important to know that when we have a process that is going to be based on a steady state, means independent of time. So the time does not matter. So the process is going to be complete, but independent of time. Okay, we call it a steady state. All properties are contained in time for a control volume at a steady state. The left-hand side of this equation will go to 0, okay? So the change in mass within the control volume over dt equals 0 for control volume at a steady state. Okay? So that will be the fundamental work that we're going to be using to solve thermodynamics problems. So conservation of a mass demo, when this is 0, then we have a conservation of mass rate n equals to sum of the mass rate out. So sum of the m dot means mass flow rate, okay, over time. So here, if you have a steady state, what is the outlet mass flow rate? Okay. So we have 2 inlet and we have 1 outlet, okay? So coming into the control volume and then leaving the control volume, the mass. Okay, we're talking about. If a steady state, what is the outlet mass flow rate? So the sum of because of the conservation of mass, the sum of the m dot 1 and m dot 2 will be the outlet mass flow rate. Great. Next, energy rate balance. Okay, energy rate balance, because we are going to incorporate the internal energy heat transfer into the control volume, the work leaving the control volume, or we call it a work rate, okay? W dot means rate of work. Q dot means heat transfer rate. And then M dot is a mass flow rate. We're gonna have internal energy. We're gonna be dealing with kinetic energy and potential energy. And some assumptions we might just ignore the potential and kinetic energy, okay, in some situation. All right, so this is a energy rate balance, okay? So the rate of the energy contained within a control volume and the net rate at which energy is being transferred in by heat transfer at time t, that's a Q dot, and then the energy going into the system is positive, and then the work leaving the system is negative. The net rate at which the energy is being transferred out by work is going to be negative, and the net rate of energy transfer into the control volume accompanying mass flow, that is positive. Okay, so next we're going to look at also the inlet. We're going to have the inlet mass flow rate. It has the internal energy, kinetic energy, potential energy, and then that potential energy is the elevation, okay, Z times the gravitational acceleration. So from physics class, you have learned about the potential energy, kinetic energy, and possibly internal energy. Okay. All right, so the expression for work is given as such. The work due to the control volume, or maybe you have a propeller, or you have a device that is going to add energy by doing work to the system. So we call it W dot CV within the control volume. And then the M dot at the exit and mass flow rate, and then the pressure at the exit and the specific volume, minus M dot I PI VI. W dot CV accounts to work associated with rotating shaft, okay, or propellers or anything that is going to stir the water and so on. Displacement of the boundary and electrical effects. W dot M dot EPEVE is called the flow work, okay, at the exit. And then this M dot I PI VI, we call it the flow work at the inlet, flow work. One thing I want you to know that for this chapter especially, okay, and previous chapter as well, being consistent and unit is very, very essential, because without the units being balanced, your answer will be way off, okay? So we're gonna talk about that, unit conversion. So steady state, again, control volume and steady state, all properties are unchanging within time, okay? That's a steady state. And we have the mass rate in, mass rate out, and then this steady state control volume, the left-hand side of that energy balance is going to be 0. So for a steady state control volume, the left-hand side is going to be 0. So if you look at that, diagram, we talk about the amount, the heat transfer rate into the control volume, and then minus the work rate that is leaving the control volume. Sum of all the, because we are dealing with open system, so we're going to be using what? Enthalpy, okay, instead of internal energy. So M dot IHI plus inlet velocity square over 2, potential energy minus the exit, okay? So let me just go to the assumptions. To simplify the analysis, many simplifying assumptions are made: a steady state, one-dimensional flow, equilibrium property relations at the boundary. Kinetic and potential energy changes can be neglected. Okay, so that's a good assumption, that because compared to enthalpy, and even the kinetic energy might be small, very small compared to potential, or we call it the enthalpy. Kinetic and potential energy changes can be neglected when they are small relative to other energy transfers. Okay. So W dot CV equals 0 if there are no rotating shaft, if there is no work done according to physics law, if there is no work done, no displacement, no change in internal energy of the system, so there is no work, okay, displacement of boundary or electrical effect. Q dot CV equals 0 if outer surface of control volume is well insulated, adiabatic, or the outer surface area is small, or the temperature difference between the control volume and surrounding is negligible, or if mass passes through the control volume quickly, okay? But like we have high speed PDV. So we have isentropic relationship, and we have a sample of gas. We open the valve that we have a air, pressure, and then we have an assembly, so we can just have a sample of gas. We compress it at higher speed, and then we have a curve. We call it isentropic curve, and we wanted to know whether it's reversible or not. We're going to open the bleeding valve, so the piston has to come back to its original position where it's started, so we call it reversible. We're going to talk about the reversible process, okay? So then we have to find the work under the area or under the curve, which is, we call it the area, shaded area, because we're going to have a compression and expansion, okay? Compression high speed at high speed, okay? So we're going to go to, this is beautiful concept of nozzles and diffusers, okay? Nozzles and diffusers, because we're going to be using that in the wind tunnel test, and also we're going to use it in turbine design and so on. Okay? So nozzles and diffusers. This is if it converges like this, okay? Converges to a smaller area from large area. So the velocity at exit is going to increase, while the pressure will at the exit or at point 2 is going to be lower than the inlet pressure. Okay? So when we have a nozzle, this is an example of diffuser. So we have a velocity at point 2 is going to be less than the velocity at point 1, but the pressure is reversed. So pressure at point 2 is going to be greater than 2. So have the understanding of what nozzles and diffusers are. Okay, all right. So we will be using in an application in thermodynamics devices such as turbine, compressor, pump, heat exchangers, or we call it recuperators, and throttling valve, which is, let's see. All right, so if we have a wind tunnel test, for example, here, that's a wind tunnel device. Nozzle and diffuser are often combined, for example, in wind tunnel. So we wanted to determine the aerodynamic shape of, or drag, to see how we can minimize the drag in testing a car or aircraft or wing, or we have a blade. We have a cascade blades, for example, or airfoil blade, and we wanted to test them to see what will be the angle of attack loss. And that is something that in advanced thermodynamics, it's a project that the students work on. They call it cascade blade, or we have a blade that is airfoil, or it has a shape of chamfer. It has a chamfer or camphor. All right. So this is the intake. Okay, intake, and then we have a honeycomb of gauge, and then working section. Okay, and the model and diffuser. That's a nozzle diffuser, and then we have a motor. Okay. All right. So. And normally, if we have even air duct, okay, if you have a blower, whether it's a square duct or a round duct, you can send the air through this air duct, or say we have an air conditioning unit at home, and we have all kinds of air duct in the house. So when you send the air through that conduit or square duct or round duct, we need to measure the pressure or velocity or temperature and so on. One method that we use in the laboratory to determine all those properties, we call it the pitot tube. Okay? Pitot tube. And the pitot tube is going to give us the information about the velocity. Okay, if it's a you place the pitot tube, which is, it has a propeller inside the air duct, and then if you have a vane anemometers, you have a meters, you can directly measure the flow inside the air duct. But in order to have a fully developed flow, we need to put a strainer or some kind of cascade type of mesh, so that the air that goes through it becomes fully developed before it hits the cascade blades that we're going to measure the angle of attack loss. because in Bernoulli, we're going to be talking about the Bernoulli equation. Bernoulli equations indicated that the change in pressure is equal to dynamic head. Dynamic head is called the 1/2 rho v squared. 1/2 of rho, which is density, and then v squared velocity, and that the pressure, the change of pressure, we call it a stagnation pressure minus the static pressure. So that will be discussed later on when we are dealing with the flow inside the conduit or air duct. Okay, so rocket nozzles are typically converging, diverging type of, using the nozzles and diffuser. So converging and diverging nozzles, compressible flow. Again, I'm going to go back to Bernoulli. Bernoulli said that if the flow of air is supposed to be compressible, right? But it's not really compressible at certain Mach number. If it's if the Mach number, the flow is less than 0.3, because we have a subsonic flow, we have a sonic flow, we have a supersonic in terms of speed. So the air is supposed to be compressible, but at certain Mach number, it's considered to be incompressible. Okay, incompressible. Because when the air or ideal gas is compressed, that means the density will change. But if it's incompressible, then the density doesn't change. Okay, so here, and also I would like you to watch, because we don't have time to go over this video. Please, this is really a nice link to YouTube to watch the video. And these two, I'll leave it up to you to do that, okay? Because we don't have enough time to watch these videos here. The thing is that when I had some difficulties posting the Friday's lecture, because it was a bit long, and then I tried to upload it to Blackboard, and the Blackboard will give me at the end an error message saying that it's too long. Your video is too long, it's not acceptable. So I had to then post it on my YouTube account, and then I send you the link. Okay, sorry, but it took me a long time because I created a new account in YouTube and it didn't work. But my old YouTube account that I use for computer-aided design CAD classes, it worked. So I posted. I hope you were able to watch that. Okay, I had some difficulties with technology. Okay? Anyway, so we're going to start with the first thermodynamic device. It's called turbines, okay, turbine. We have a gas turbine, okay, gas turbine, and we want to, if you want to work for solar turbines, so it's good to know the language of thermal sciences, which is, when we say thermal sciences, means alternative energy system design, introduction to thermal sciences, thermodynamic, heat transfer, fluid mechanics, and anything that is related to energy, okay, energy. That will be a part of mechanical engineering, a branch of mechanical engineering, which we call it the thermal sciences versus design, okay, the design, the other branch. Great. But for undergrad, everything is going to be just, it's combined, so there is no separation. But when you go to grad school and so on, then you have to just figure out which area you wanted to concentrate. So this gas turbine, or just turbine in general, use a vapor and gas turbine power plant, jet engine, and in power plants and jet engines, superheated the steam or gas enter the turbine and expand to a lower exit pressure as work is developed. The blades are attached to a shaft free to rotate. Yeah, so these are the stationary blade, and that's a rotating blade, so it's going to do work. Okay, turbine in engineering. Okay, so we have the some pictures, beautiful picture, and this is the cutaway view of jet engine cross section. All right, so we have air inlet, we have a combustion chamber, because later on, if you have an upper division in thermodynamic course, they're going to talk about the cycle. So you need to have a pump, compressor, and then combustion chamber, and then we have a condenser for evaporators, And then we have the mechanical work that is going to generate electricity, right? Mechanical work. All right, so this is what we have, and this is the shaft, and this is the work of the shaft. W.CV, the axial flow compressor, and is component of a jet engine, and so on, okay? And these are the more picture of reciprocating compressor. Okay. And we're gonna continue on this. All right, system with multiple devices, gas turbine, jet engine. Gas turbine, jet engine utilizes the compressor, turbine, nozzle. So to build or design the gas turbine jet engine, you need to have the knowledge of compressor, turbine, and nozzles. Both are powered by the energy produced during combustion. Okay? So that's where we add heat or energy to that combustion chamber. It costs money. So that's why we have a fuel. And then if the fuel is too expensive, trying to go from one part of the world to another part of the world with aircraft, so that you have to spend a lot of money for the fuels, right? All right. So because you got to get this beautiful machine, or I call it thermodynamic device, to work. All right, so please watch. Okay, this is a beautiful documentary. So gas turbine are also used in power plants. So try to just find times to watch these videos. Okay, all right. So at the end of this section, you should be able to define the following terms: heat exchanger, throttling device, and list typical modeling assumptions of heat exchanger and throttling devices. Analyze problem with the heat exchangers or throttling devices using the mass and energy balance. Perform an energy balance for connected devices. Okay, so this is an example of heat exchanger. We're going to have direct heat exchanger. We have a parallel flow heat exchanger. We have a counterflow heat exchanger. And these are the example of, we call it a direct contact here for figure A mixing chamber in which hot and cold streams are mixed. Then we have a counterflow heat exchanger because we have a shell or two tubes, these tubes, and within that tube, so the flow go in and then goes in this direction, and then inside the pipe, we have a flow going opposite of this. So this is called the counterflow heat exchanger. Tube within a tube counterflow, a gas or liquid stream is separated from another gas. A gas or liquid stream is separated from another gas or liquid by a wall through which energy is conducted. Heat transfer occurs from the hot stream to the cold stream as the streams flow in opposite directions. So that's an example of counterflow heat exchangers. If you're planning to take another course in thermodynamics, they're going to talk about it in details, counterflow heat exchangers and parallel flow. Another name for this, they call it recuperators. And also we have a radiator, right? A radiator in your car, but it's an heat exchanger. All right, so this is the heat exchangers in engineering, and a boiler and car radiators and a heat sink. Okay, the back of your computer, in order to dissipate the heat, we call it a heat sink. So we have a fan so that we can get the heat from the component. We call it electrical component because it's the heat is going to damage the component, so that we need to get rid of the heat that is generated within this compartment of the computers or any other electronic devices. Okay, so this is an example of a throttling devices. When you partially open, you use if significant reduction in pressure is required, so that you can just, if the pressure is high, you can just like a bleed valve, so you can open it slowly, and then you can just reduce the pressure. Okay. And then this is in terms of simple vapor power plant. We're going to have the pump, and then the pump is going to send the fluid to the boiler, and that's where the heat is input into the combustion chamber or boiler. And then we have the turbine, and the work of the turbine, the rate of work, then is going to run the generators. Okay, we're going to produce electricity. So, and also we have, since we are dealing with a closed system, we need to add condenser. Okay, we need to add condenser to that, so that will dissipate the amount of steam, for example, if it's because it's going to damage the pump. So we need to remove all this, vapor, okay, vapor, liquid vapor. So we need to add the condenser to that, okay? That's part of the system. So that's what we have in here. All right, so I think this is the end of chapter 5, but let me just review my notes, okay, and some example how to calculate the mass flow rate or the work rate for turbines, for compressor, and so on, okay? So let me see if I can connect this. Okay, stop the share. All right, that is, oops. Oh. Okay, let me see if I can go here. And this is that. All right, so, and then where are we now? Okay, let's see if I can go to, can you hear me, guys? Yeah?
Yes.
Okay, thank you. Thank you for a second. I thought maybe, the microphone was not on. So let me see if I can go to, oh, I know what the problem is, because I should not have a virtual background for this, okay? Virtual background, I have to change that to none. Now we have the problem. See that? The technology is unbelievable. Okay, so this is where we are. Yeah, okay. Okay, let me just move this a little bit higher. All right, sorry about that. Can you see, guys, this? Can you see that? Okay. So let me just quickly go over this again. We already talked about the turbine is a device which in which work is developed as a result of gas or liquid passing through a set of blades attached to a shaft free to rotate. Turbines are widely used in power plants, gas turbines, and aircraft engines. So if somebody wants to study more about these thermodynamic devices, you have to take advanced courses in thermal. In these applications, superheated steams or gas enter the turbine and expands to a lower exit pressure as work is developed, okay? So let's look at the one example and then the units, okay? Unit that we're gonna incorporate into this. Steam enters a turbine operating at a steady state, okay? A steady state, that means the left-hand side, the net amount of mass at the controlled volume with respect to time is 0. A steady state with mass flow rate of 4,600 kilogram per hour. The turbine developed a power output of 1,000 kilowatts, okay? The turbine developed a power output of 1,000 kilowatts. At the inlet, pressure is 60 bar, the temperature is 400 degrees C, and velocity is 10 meters per second. Then at the exit, the pressure is 0.1 bar, the quality is 90% because of the mixture, correct? A region. And the velocity is at the exit is 50 meters per second. And determine the rate of heat transfer between the turbines and surrounding in kilowatts. So that's the question. We want to calculate the rate of heat transfer, Q dot. Okay, so this is just the schematics of the turbine, like we call it the nozzle, and it's a diffuser, this is diffusers. I'm sorry, diffuser. M.1, P1, T1, V1 is given, and then the W dot CV is the work of the turbine is given for the control volume, 1,000 kilowatt, the power output. So potential energy and kinetic energy can be neglected compared to the value of other properties. So now that we have this statement here, a steam entered the turbine, and we wanted to calculate the heat transfer rate. Okay, the heat transfer rate is this here. So this is the energy balance. From energy balance, we have Q dot CV equals W dot CV plus M dot change in enthalpy plus kinetic energy, okay? V squared minus V1 squared over 2. So, and then if you look at the PV diagram for the inlet pressure, which is a 60 bar, and then we have the exit pressure, which is 0.1 bar, reduction of the pressure, correct? All right, so because the pressure is decreases, because we have a diffuser. So we have the PV diagram, and all we have to do is, because we are in a region of mixture, okay? So we need to calculate the enthalpy using the quality and the, from the table T-3, we can find the change in enthalpy, not internal energy, okay? Because it's an open system, okay? We're not going to use CV, okay? And here we don't need to use CV, CP because we're dealing with steam, okay, with water. So it gives you error, law of errors if you do that. So we need to use the information from the table. So at the temperature of 400 degrees Celsius and pressure of 60 bar, state 2, and then we can go to table T-4, and then we can calculate, we can just copy down this value, okay, the H1. So we go to table T-4 for the given inlet information. H1 is this value here for enthalpy. And then if for state 2, it's a two-phase liquid, okay? It's a two-phase liquid because this, if you just draw a dashed line coming down to this region, maybe it's a little bit, I should have expanded this. Since this point 2, state 2 is in a two-phase region, we need to use the liquid and vapor, okay, for the mixture. So in order to determine this enthalpy at the state 2, this is the basic formula. Remember, we use this formula to determine the internal energy or specific volume. So H2 is HF2 plus quality at the state 2 times the change in enthalpy, which we call it HFG. But you have a value for HFG, but we can just say HG2, the vapor portion, and then the liquid portion. So if you go to table T-4, or I'm sorry, T-3 for a state 2, T-3. So we can just get HF2, which is 191.83, and then the quality is given 90%, and then we can copy down this information from the table. So we have a H2, okay, and the unit is kilojoule per kilogram. So remember that for chapter 5, you're going to be dealing with this kind of information over and over, okay? All right, so then we have, I'm going to just, because in this formula we have the W dot CV, which is given to us, okay, the power of the turbine, okay, out, and then the change in enthalpy from the table, and the velocity is already given to us, the exit velocity and inlet velocity is given. So separately, I'm going to, since I already have the H2 minus H1, okay, H2 minus H1, I'm going to just come up with a number, which is a negative number, okay? H2 minus H1 is minus 831.8. And then we have the kinetic energy here is V2 squared, which is 50 squared minus 10 squared over 2. Because the unit is what? Meters squared per second squared, okay? The unit for this is meters squared per second. Because the final answer we want to have in kilojoules, or we want the kilowatts, okay? The heat transfer rate has to be in kilowatts. So in this term, okay, we have a term here, we have a term there, and then we have a term here, and we have a mass flow rate, okay? All right, so mass flow rate is a kilojoule per kilogram. I think that is given to us, okay? And kilogram per hours, okay? Because it's a rate, even a kilogram per second or kilogram per minute or kilogram per hour. So that is given to us in here for the inlet. It says the M.1 is 4,600 kilogram per hour. Okay. So you can see that the units are all over the place, okay? All over the place. Well, we need to balance that. So if I look at piece by piece here, so we know that the change in enthalpy is kilojoule per kilogram, and then the kinetic energy is meters squared per second squared. we know that kilogram meter per second square is equivalent to 1 Newton, okay? Kilogram meter per second square. Where this came from, the kilogram? Because the Newton law, the force, right? Force is equal to, let me see if I can write it down here. Okay, force from Newton law, we got mg. Mass is kilogram, g is meter per second square, okay? All right, so that acceleration due to gravity is meter per second square, mass is kilogram, or we call this weight also. In the static course, we call it the weight, because if the mass is given, we need to convert it to weight because this is equivalent to 1 Newton, okay? 1 Newton. All right, that's something that please practice so you get used to this unit conversion. Otherwise, your answer will be, you know, way off, okay, all right. So then we have to multiply this or divide by 1,000 Newton meters because a kilojoules, 1 kilojoules is 1 Newton meters, okay? 1 kilojoules is 1 Newton meters. So, and if you look at the units here, okay, Newton meters, okay, Newton meters, and we have, this should cancel because we need to have we need to end up with a kilojoules per kilogram for the kinetic energy, kilojoules per kilogram. So that is this second square here, because this is a, you know, just we call it in a fraction that we have numerator and denominator, so that this second square goes to the numerator and that cancel with this here. Okay, all right, so and then we have Newton will cancel with a Newton here, and meters times meters is a meter square, and meter square and meter square cancel. Okay, meters times meters is going to be meter square, so that numerator and denominator will cancel each other out. So the leftover is kilojoules per kilogram. So that is what we need. Okay, great. Now we go to here, the original formula here. W dot CV is a kilowatt. Okay, it's given to us. And then we have the mass flow rate is at 4,600 kilogram per hour. 1 hour over is equivalent to 3,600 seconds. So we can cancel hour with hour. And then here we have kilogram. Okay, we got kilojoules. This is kilojoules per kilogram. So, and then we have the minus 831.8. That was a change in enthalpy, which we have already determined that here. Change in enthalpy, which was minus 831.8. I'm substituting into this formula here. And then we're going to have the value for the kinetic energy, in which is energy. So it's a 1.2. It's a 1.2 kilojoule per kilogram. So, so far so good. So we have the minus 831.8 plus 1.2, and then we end up, if we do the units, you know, make sure that the units are all cancel each other out. And we know that 1 kilojoules per second is 1 kilowatts. So then kilojoules and kilojoules will cancel each other out. So then we have kilojoules per second, okay? All right, so kilojoules per second means kilowatts, okay? Kilojoules per second means kilowatts. So then you end up with minus 61.3 kilowatts. So this is, I just wanted you to, I'm gonna give you a homework problem that will be a turbines and compressor homework. So make sure that you check the units for each term and the final answer. If it says we want you to find the volume or heat transfer rate in kilowatts, so make sure the units will balance. Okay. All right, so that's what we have in there. Okay. Any question, guys? Do you have any questions? No? All right, so I'm going to assign homework for chapter 5, okay? The best way to learn about control volume or mass flow rate or conservation of mass is to solve application problems. Then all these formulas that we call it governing equations will be, you will be able to solve for unknown. The chapter 5 should be fairly simple, okay? It's not that complicated. All you have to be careful with the units. That's all I wanted to give you advice, that if your answer is way off because of the units, okay? All right, so in engineering, the language is this: make sure that the end result that you have is with a unit that they're asking you to determine that properties. If your value is way out of the pictures, or we call it outliers, that is too far off from the reality, then in that case we say we have problems with units. And many accidents happen in terms of design because they forgot to convert the units correctly. Okay? Like in a dynamics class, I asked the student to design a runway and what will be the length of the runway for Boeing, or to be able to take off. Somebody came up with a unit of 2,000 kilometers. Okay, and I said, wow, that's a lot of money we need to spend to design that runway, right? All right, so anyway, let me see where I'm at. All right, guys, let me see. I'm trying to, I think my is okay. And okay, the next topic will be on share screen. Okay, see if this is, no, I have to minimize this or escape from here. Cancel. Trying to bring another PowerPoint. Okay. I want to exit from here. And then, okay, chapters. And guys, do you see this here? Do you see this chapter 6? Yeah. I don't think. No?
No.
No, I think, all right, so I think I need to go back and share this, okay? All right, so share. Okay. All right, so if I go back to here, chapter 6, okay, share a screen, and that will be here. Okay, it's better now? All right, can you see it? All right, can someone confirm?
Yeah, we see it.
Okay, thank you. Thank you. That's better now. Okay, again, chapter 5 was all about the conservation of mass. The previous chapter, we talked about the conservation of energy. And now on chapter 6 is the second law of thermodynamics, which is the entropy, okay? Entropy, the law of entropy. And also we have already on chapter 3, we talked about the cycles, like a refrigeration cycle, power, or the engine or the cycle or power cycle. And then we had the AC or air conditioning cycle. And chapter 6 is going to elaborate more in terms of reversibility and irreversibility, irreversibility versus reversible. And then the Carnot engine is also, they call it the best engine. The Carnot said that the best engine that he came up with, it's called a reversible engine, okay? Reversible, that means it's going to come back, all the surrounding and all the property will come back to its original state. That's what we call a reversible. Like if we have a sample of a specimen that we pull for tension, And if we remove the load, if it didn't pass its elastic region, it should come back to its original position, which we call it no damage. So they call it reversible. Okay, you can just get the specimen that it's ductile, for example, not the brittle material. Ductile material will stretch, but it stretch up to a point that if you remove the load, the specimen will come back to its original state or position. All right, so let's talk about the chapter 6 for like 5 minutes, and then we'll continue this tomorrow, okay? Because I don't want you to get headaches. So chapter 6 introduce the second law of thermodynamics, identify valid processes as those that satisfy both the first and second law of thermodynamics, discuss thermal energy reservoir, reversible and irreversible processes, heat engine, refrigerators, and heat pumps, describe the Kelvin and Planck and Clausius statement of the second law of thermodynamics, to discuss the concept of perpetual motion machines. I have a nice video about the perpetual motion machines, okay? So we're gonna watch it. Okay, all right, so apply the second law of thermodynamics to cycles and cyclic devices, apply the second law to develop the absolute thermodynamics temperature scale, which is a Kelvin and Rankine. Describe the Carnot cycle. So we're going to put emphasis on Carnot cycle. Examine the Carnot principle, idealize Carnot heat engines, refrigerators, and heat pumps. Determine the expression for the thermal efficiency and coefficients of performance for reversible heat engine, heat pumps, and refrigerators. Okay. All right, so this is introduction to the second law. See that here we have a hot coffee. A cup of hot coffee does not get hotter in a cooler room. So it transfers the heat to the surroundings. So it's not possible, correct, to warm up the hot coffee in an environment, we call it a temperature, room temperature. These processes cannot occur even though they are not in violation of the first law, so which is a conservation of energy. But energy cannot be created nor destroyed, but can be converted from one form to another. So if you, in an electrical circuits or in a wire, a current can flow through the wire, but you cannot put a heat next to a wire and expecting to have electricity, okay? So transferring heat to a wire will not generate electricity. Transferring heat to a paddle wheel will not cause it to rotate, okay? Transferring heat to a paddle wheel will not cause it to rotate. So these are the language that we need to pay attention, and that the transfer of heat to the surrounding, it happened because that's the law of heat transfer from the hot surface to a cooler surface, okay, or cooler area, or to the surrounding. And then it says to identify the direction, major uses of the second law. It says these are the major uses. To identify the direction of the processes. The second law also asserts that energy has quality as well as quantity. The first law is concerned with the quantity of energy and transformations of energy from one form to another form with no regard to its quality. The second law determines the quality as well as the degree of degradations of energy during the process. The second law of thermodynamics is also used in determining the theoretical limits for the performance of commonly used engineering systems such as heat engines and refrigerators. All right, so it says one-way direction, process occur in a certain direction and not in the reverse direction. So for example, the hot coffee mug, it just transfers the heat in one direction, okay? You cannot just have the cup of coffee and say, I want that naturally to be warm. And we wanted the heat will go in a reverse direction. No, it will go in one direction. A process must satisfy both the first and second law of thermodynamics to proceed. Degradation of energy, the processes by which energy becomes less available for doing work, compare conservation of energy, dissipation of energy to heat sink, for example, designing heat sink, and so on. All right, so this is, I'm gonna just stop, just go over this and then stop right here. Thermal energy reservoir, okay? Just we talked about the heat sink and so on, okay? Remember the dissipating the heat from the device that it's gonna cause or damage the component, like in electrical circuits or the PCB board. It's the vitals, okay? Because we need to do that, otherwise it's the system will just collapse. So bodies with relatively large thermal masses can be modeled as a thermal energy reservoirs. Okay, it's like a heat sink reservoir. So thermal energy source from the hot environment, and then we're gonna just sink it to a cooler environment. So a source supplies energy in the form of heat and sink absorbs. Okay, so we're gonna be talking about the heat engine and refrigeration cycles and other cycles. Okay, all right, so I think this is good enough for today. I'm going to post homework, which is due not tomorrow, it's going to be due Thursday. Okay, I might assign homework for chapter 5 and 6. Okay, 5 and 6 because we are running out of time. And then chapter 6 was the last chapter for thermodynamics. Then we're going to go to fluid mechanics. Hopefully on Thursday and Friday, we're going to talk about the fluid mechanics. And then next Monday, there will be a second midterm exam. Sorry that this is I'm not comfortable with the summer session with 3-week sessions, but it's going so fast. So then we have a few days to cover the heat transfer, which is the 3 modes of heat transfer called conduction, convection, and radiation. Okay, we're going to touch on the surface of all 3 modes of heat transfer, and that will be sufficient for this course. Let me see if I can stop the recording.